Hello everyone. Today's topic is queue implementation using linked list. As we have seen in the last class, arrays and linked lists are linear data structures which allows insertion and deletion at any locations. In case of arrays, you can use its index variable to insert or delete element at a particular location. In the case of linked list, you can use the links available in the data structure to traverse through the linked list, and it's possible to insert and delete elements at the beginning or at the end or at any in between locations. So if we want to restrict the insertion and deletion operation so that it takes place only at the beginning or the end of the list and not in the middle or at any in between locations, then based on this condition you can define two new data structures. The first one is a stack and the second one is a queue. In the case of a stack, as we have seen, you can insert and delete in the beginning of the list, or we call it the top of the stack. A queue is a linear data structure in which the items are added at the rear end and the items will be deleted from the front end. So based on that condition, you can say that queue is a FIFO data structure, the first in first out data structure. It's also called a FIFO list. So elements are arranged in a queue in the first in first out order. The first element that is going into the queue will be coming out first. So the first inserted element will be the first deleted entry in the case of a queue, whereas the last inserted element will be the first deleted entry in the case of a stack. The definition of a queue: a queue is a linear list of elements in which deletion can take place only at one end, called the front end, and insertion takes place only at the other end or the opposite end, which is called the rear end. In case of stack, we have seen two basic operations, a push operation and a pop operation. The push operation was basically the insert operation, inserting an element at the top of the stack. Pop operation is a delete operation, which is deleting an element from the top of the stack. In the same way, there are two basic operations in the case of a queue data structure. You have an enqueue operation, which is basically an insert operation, and a dequeue operation, which is a delete operation. There is a small difference compared to stack. Enqueue operation or the insert operation happens at the rear end of the queue, whereas the dequeue or delete an element from the queue happens from the front end of the queue. So in case of queue, one end is always used to insert the data and the other end is used to remove the data or delete the data. Queue follows the first in first out methodology, or the data item stored will be the data item stored first will be accessed or deleted first. So as we have pointed out, queue has two pointers, a front pointer and a rear pointer. Using the front pointer, we'll be deleting an element. Using the rear pointer, we'll be inserting an element. So in the example queue shown here, 10 was the item entered to the queue first, then 20, then 30, then 40, and then 50. The first deleted entry will be 10 in this case. So in case of queue, front will be always pointing to the first element and rear will be pointing to the last element. This is how we insert an element and delete an element from a queue. Queue equal to new queue means you will be creating an empty list. Enqueue operation, you add A. Enqueue B, you insert one more element. Enqueue C, you insert one more element C. Enqueue D, you insert one more element D. So now the queue will be containing A, B, C, and D. Elements of a queue are processed in the same order as they are inserted into the queue. Here A was the first element that is inserted onto our queue. So that will be the first element to delete from the queue. So if you ask for a delete DQ element, delete operation, then the element that will be coming out will be A. DQ operation again, the element that is coming out will be B. Now what is left in the queue is C and D. You add one more element, then it will be C, D, and E, and so on. Queue can be represented in a program or in computer using an array or using a linked list. The array implementation of queue, we have seen it already. Today we will see how we can represent a queue using a singly linked list. Just to recap the array representation, there are two pointers called front and rear. Front will be pointing to the first element and rear will be pointing to the last element that is there in the queue. Here, in case of array representation, you have to define a maximum size for a queue. So, based on that size, you will have a limitation. That is, you can enter only that much size of that many number of elements onto the queue. Whenever an element is deleted from the queue, you will increment front. Whenever an element is inserted into the queue, you will increment rear. So it is just order of one operation for delete and as well as insert element. But you can see that in the case of an array representation, you cannot utilize the entire size of the array because if, for example, in the above array implementation, A, B, C, and D elements have been inserted, you can insert two more elements. But even if after you delete A, B, and C, for example, you have deleted some three elements A, B, and C, you cannot insert anymore because you have already free space in your queue, but still you cannot insert. These sort of disadvantages of array representation can be avoided by utilizing linked list representation of queues. This is just an illustration of array representation of queues. You have an empty queue initially, then front will be pointing to 0 and rear will be pointing to 0. You insert three elements A, B, and C. Front will be pointing to 1, rear will be pointing to 3. Then you delete one element, front will be incremented. You insert two more elements, rear will be incremented, and so on. Now queue is full. In this case, we have B, C, D, and E elements. But now, if you try to insert one more element, you will get an error message that queue is full. But you have already free space at this location. Now coming to the linked list representation of a queue. The advantages of linked lists over arrays can be utilized in case of this implementation as well. In a linked list, we have a data field as well as the next pointer or a link field. So in the data field, you can store the elements of the queue, and the next pointer or the link field, you can use it for pointing to the next element in the queue. Here the enqueue operation is done by inserting a new node in the tail or the end of the list, and dequeue operation is done by removing the element from the beginning of the list. So you have, in addition to the head pointer, you have two more pointers, front and rear. The front will be pointing the first node in the linked list, and rear will be pointing to the last node in the linked list. So if you would like to add one more element, you insert one more element, or the enqueue operation is done like inserting a new node at the end of the list. Dequeue operation or delete operation from this queue implementation is done by removing the element from the beginning of the list, which is very similar to the operation in the case of a stack implementation using linked list. So the delete operation is same as that of stack implementation of linked list, but the insert operation is just opposite. That is, you will be inserting at the end of the list. Insertion of an element at the end of the linked list this we have seen while talking about singly linked list. Consider a linked list of 3 nodes. We have 3 nodes. You have a pointer head which is pointing to the first node. Then you have 3 elements, 10, 20, and 30. These are the data elements. And you have link fields pointing to head is pointing to the first node. Then first node's link part is pointing to the second node. Second node's link part is pointing to the third node, and third node's link part is pointing to null to specify that that is the end of the list. Now we want to insert a new node temp with value with data item equal to 40 at the end of the list. This is how it is being done. You create a new node temp and you attach that value 40 onto the data field, and you traverse through this list and insert, or the last node's link field is attached to the temp. That's how you insert an element at the end of the linked list. The same thing you can do it in the case of queue implementation using linked list as well. So the enqueue operation is, you have a head pointer. You take a new variable PTR, which is same as the head pointer, or which is a pointer to a node, and you traverse through the links until you reach a null pointer to see that you have reached the end of the list, because in the case of an enqueue operation, you are inserting the element onto the end of the list. So this is how you do it. While PTR pointer link not equal to null, PTR equal to PTR pointer link. So in the first step you will traverse from first node to the second node, then second node to the third node to the fourth node, and so on. So in the previous case, if you want to insert this 40 element onto the list, or the enqueue operation of the value 40, which is done like you attach PTR pointer link equal to temp. You have reached here PTR pointer link was null previously, to specify that it is the end of the list. Now you attach this statement PTR pointer link equal to temp. So this link is created. This link is not null now. This link is pointing to the next node, which is 40, and temp pointer data equal to item. So item is our value, that is 40. Temp pointer data equal to 40. Now you have correctly attached your new entry onto the list, or right now this is happening like a queue. This was the first item, second, third, and fourth. So if you access your elements using head pointer, you will get the first item that you are getting is 10, then 20, then 30, and then 40. So it is following the FIFO structure. The dequeue operation is, as I have told, it's very similar to the stack operation, delete operation, or pop operation in case of stack. Only thing you need to check is whether your queue is empty or not in case of dequeue operation. If your queue is empty, head is directly pointing to null. If head is equal to null, you print empty queue. Otherwise, you access your element. This is your deleted element, that is head pointer data, and you move your head pointer to the next node. So this is how you do it. Head was previously pointing to your first node. Now you attach head to the next node. That's it. Head to head pointer link. So now head will be pointing to node 20. So means that in your link list you have only 3 entries, 20, 30, and 40. Means that this value is being deleted. So there also it is following the FIFO order or FIFO structure. So this is how you implement your queues using linked list. So the implementation of queue using linked list is a very easy operation compared to implementation using arrays. In case of implementation using arrays, you have some limitations, like you have to set a maximum size for a queue, and you need to, while inserting, you need to check whether you have reached your maximum size or not. But in case of queue operation using linked list, there is no such maximum size limitation. Only limitation what you are going to have is your memory overflow. And in case of delete operation, of course, there is a underflow operation. That is, if your queue is already empty, you cannot delete anymore. So once again, enqueue operation. In case of enqueue operation, you traverse through the list and insert your entry onto the as the last entry, as the last node in the list. In the case of dequeue operation, you just delete the first node. So that is the implementation of queues using linked list. Thank you.